So potential energy and the work done by conservative forces. We're actually talking about gravity. That's really what the topic here. When you, for example, standing on top of a diving board, ready to jump into the water or step off the diving board, there's the water here. At this point, because the height is larger, you actually have larger potential energy. Well, larger energy because that distance, the height, to get to that point will take a lot more actual energy than to get to this point. Or if you're holding in your hand 1 pound and you drop it from the second floor on somebody's toe, it's going to hurt a lot more if you dropped it from 1 meter above the ground. So the higher you are, the more potential energy you have. Potential energy is defined as mass times gravity times height. And notice the larger the height is, the more energy that you have. So if somebody is standing on a diving board here and jump to the water right here, at the top you have more potential energy because your height is larger. If I use the water's reference here, and the diving board is 3 meters high, we'll say 3 meters, your potential energy is mass times gravity times 3. When you hit the water, your potential energy is 0 because the height is 0. So now, the work done by conservative force is defined as the initial potential energy minus the final, the initial minus the final, not the final minus the initial, because you have more on the top initially than in the bottom when you land there, unless somebody fires you up in the air there, then you're going against gravity. But the work done to gravity, you're going to have a higher value on the top than the bottom. So the work is going to be the initial or potential energy initially minus the final potential energy. Our book defines the change in potential energy as mu F, or final potential minus the initial. So that means the work now can be written as negative delta U. Negative. Because it's the initial minus the final, not the final minus the initial. So just remember there's a minus sign to indicate it's the initial minus the final. Let's take some examples using these equations. That's this one and this one. These are the two equations. Let's try some examples with them. We'll use that example. Find the potential energy. If this person has a mass, the mass of this diver is 65 kilogram. Standing on top of a 3-meter diving board, and let's calculate the potential energy at the top, and let's use the water as reference, and how much work was done by gravity. Well, the work done by gravity is equal the initial minus the final. Well, potential energy is what? The initial is the mass times gravity times the initial height. The final is the mass times gravity times the final height. If I use the water as reference, what was my initial height? Where was the person standing in reference to the water? 3. So the mass is what? 65. Gravity is what? 9.8. What was the initial height? 3. Minus the mass, 65. Gravity, 9.8. What was that final height? 0. So what is the work done by gravity? It is 1911 joules, and again 2 significant digits, that's 1900 joules. Bless you. A lot of times you'll see me put Y instead of H for height. That's the same thing. You know? Okay. Another example. Let's say you decide to go mountain climbing. Mount Everest, I don't know. And I have no idea how high Mount Everest. I can Google that. Anyone?
29,000.
29,000, okay. Jason said 29,000 feet. So let's convert that to meters, Jason. 29,000 feet, right? Feet. So the conversion factor from is 3 point, some change, 3.1, 3.3, 305, 0.305. So multiply it by 0.305 times 29,000 feet. So 8,845 meters high. And you climb Mount Everest. You've been climbing for like a week, and you're at this point now. You are at the last leg of the climb. Let's say 26,000. You have 3,000 feet to climb left. So 26,000 feet, how high in meters? That's 26,000 times 0.305. You are at 7,930 meters high. So you are standing here, and your goal is to go right here. So you have to climb how many more meters now? What's the gap left for the last leg? 8845 minus that number. You still have 915 meters to climb. Let's say this person has a mass of what? 82 kilogram. Okay. Let's measure what is the change. The question is, how much work is done by gravity is going to be done on gravity against you when you're trying to climb this, to go from here to there, the last leg. What is the change in the, well, let's just talk about the change in the potential energy. Yep. What is the change in the potential energy, delta U? Well, if I just want to find the change in potential energy, if the question, what's the change in potential energy, let me put that here. I'll do both. Delta U, that'll be U final minus U initial, right? That's the change in, to go from here to there, that's how much energy you will need. If using gravity to pull you down, coming down, that'll be a negative value because you got to switch them. What is the change in gravitational? That's this one, the change in potential energy. So my U final is going to be mass times gravity times final height. Initial mass, gravity, initial height. Now the question is, what do you want to use for reference? Notice I can use sea level for reference here. I can use this for reference. I can use this for reference. It really doesn't make a difference. Maybe I'll do it twice and show you it doesn't make a difference what I use for reference. I can pick any point. If I use sea level as reference, then this will be what? The mass is what? 82. Gravity is what? 9.8. And the initial height, or the final height, which is what? 8845 minus 82 times 9.8 times the initial height, 7930. I came up with 7,35294 joules. Energy is always in joules. Now watch this. If we use the 7930 height as reference, what will happen here? Let's see what is the change in potential energy. It's going to be the mass, which is what? 82 times 9.8. And how high the peak from this point? Isn't that 915? Minus the mass, 82, gravity, 9.8, times the height, which is 0. Guess what the answer is? 7,35294. So which one we use for reference doesn't really matter. Your answer is going to be the same. You might even want to use the top as reference. While I'm at it, I'll make this. If we use the top as reference, let's see what will happen. What is the change in potential energy now? It's UF minus UI. Well, the initial one is 0 because your height is 0. Minus the mass, which is 82, gravity 9.8. But what is your height will be here? Will be a negative 915 because it's below that. And what's a negative times a negative? That's still a positive 7,35294 joules. So I can use this as reference, I can use the peak as reference, I can use this as reference, I can pick any point as a reference. The change in potential energy is going to be that much, which means I have, the person climbing that, have to supply that much energy to climb that. If this actually person sitting here and just want to let gravity pull you down, just roll with the gravity, it will be a negative because gravity will be pulling you down. How much work done by gravity to bring you down from here to there will be the same number, except will be a minus in the opposite direction. You know I come to the gym every morning, I work out. Then I defeat the whole purpose by going back to my office and have a massive breakfast, candy bars, this and that. I eat everything under the sun. Well, here's the problem with the candy bar. A candy bar, when you look at it, it might say, we'll say Kit Kat. I like Kit Kat. We have a Kit Kat candy bar, or chocolate candy bar, almond chocolate. On that candy bar, will say, when you read it, says 212 calories, capital C. And that's really, if you know there's small calorie and there's capital C and small c, and that's equivalent to 212,000 little c cal. A big C is 1,000 little c, capital calorie there. That number, there's a way to convert from calories to joules. Let's see here if we have that conversion factor in our book, because that will tell you how many joules that is. So next time we get a candy bar, we're going to think twice about it. Let's see. I love those candy bars. Energy. What do you know? 1 joule equals 0.239 cal, small cal. 0.239. 1 joule equals 0.239 cal. So when we need a candy bar that says 212 calorie, that's really how many joules? Over 1, and I'm going to convert cal to joules. 1 joule equals what? 0.239. That's equivalent to 212,000 divided by 0.239. And it's 887,029.3. I'll forget the 0.3. Never mind that. Joules. So approximately that's what? 8.87 times 10 to what power? 1, 2, 3, 4, 5. That's 1 candy bar.
That's how much energy is in that?
Yep, 1 candy bar. We're going to tell you how many steps you have to walk to burn 1 candy bar now. You're not going to like the answer I'm going to give you. Let's say somebody weighs 180 pounds. A person, 180 pounds. We have a person that's 180 pounds. Approximately, that's about 81 kilogram. I just did the math there. Approximately 81 kilogram. The question is, how many or how high you have to climb? Maybe we'll do in terms of steps there. How many steps you have to climb to burn that calorie? So you're going to climb, you're going to climb these steps. You just ate a candy bar. You're right here. If I use this as reference, how high you have to go, the height here, what is that height to burn all this energy? When you're climbing that, that's potential energy. It's mass times gravity times height. If I use here as reference, the initial one is 0, just the final one. So the energy, which is what? 8.87 times 10 to the 5 joules, should equal the mass, which is 81, gravity, 9.8, times the height. .87 e to the 5th times, e to the 5th, not times, divided by 81 divided by 9.8. Oh my goodness. 1,117 meters high. That's how high you have to go. 1,117 meters, 1.1 kilometer. So you have to go on that step machine and climb 1.2 kilometers to burn that candy bar. Now, I forgot what the height of a step is legally. It has to be a certain height. I don't know. Anyone knows what the height? Maybe I can Google it. What is the legal height of a step, like stairs? Because they have to be a certain height, especially for disability people, because they know if you make the stairs too steep, then when you step on it, you're in trouble there. Let me just go to Google. What is the height of step? Here we go. Minimum depth, 10 inches depth. Maximum rise, that's the height, 7.75 inches. That's the maximum height. So an inch is 2.54 centimeters, so let's say 7.75. An inch is 2.54 centimeter. The step is about 20 centimeter. 20 centimeter each step. So roughly one step is 20 centimeter, the height of that, which is 0.2 meters, one step. That means in 1 meter you have how many steps in 1 meter? 5 of them. 0.2, 0.2, 0.2, 0.2, 0.25. So you will have to climb, take that number, multiply it by 5. 1117 times 5. You will have to climb roughly 5,600 two significant digit steps. When
So
the
you divided 1117
by 0.2. Yep. And I round 2 decimal places, 5585. Here's the bad news. Guess how many stairs, how many steps to go from the first floor to the second we have here? About 13 steps. If you walk our stairs, count them. 12, some are 12, some are 13. So if you divide that by 12 or 13, that will tell you how many floors you have to climb. 465 story height for one candy bar. 465. I worked out for an hour yesterday, went home, had 2 ice cream sandwiches. 2, not 1. And I'm sure it's more than 212 calories. A Whopper has 1,000
I
calories.
was just thinking that, like, what about, like,
A Whopper is 4 times that. You have to climb 465 times 4, about 18, almost 2,000 floors just to kill a Whopper. So right, I'd rather be chunky. Let's try another example with potential energy. Then we'll put kinetic and potential together. Remember when we did kinetic energy last time? A car wants to pass another car, kept saying a flat road, a flat road, a flat road. What happens if the road's not flat? Then we've got to deal with the height now. And that's where the potential energy comes in. We have to deal with both. But we'll get to that shortly. Okay. We'll use this. Here's an example. When a force of 120 Newton is applied to a certain spring, we have a spring here, it causes a stretch, so it means they were pulling on a. So we have a spring, somebody's pulling on it, so they're pulling in that direction, a force of 120 Newton, and it made the string stretches. So we stretch this of what? 2.25 centimeters. What is the potential energy of the spring? Question number 1. Actually, more than one question. The question, what is the potential energy of the spring when it is part A, it says compressed by 3.5 centimeter. Part B, or number 2, expanded or stretched by 7 centimeters. Well, we know actually, I can answer question 1 and 2 quickly. Here we go. Question 1. Spring has an energy, potential energy, equals what? 1/2 kx squared. You tell me what x is, you tell me what k is, and I'll tell you how much energy.
K is the force.
K is the spring constant. So for the first one, I go, okay, it's 1/2 k. What is k? Well, that's not given to us. What is x? X is what? Compressed. By how much? By 3 point, that's negative 0.035. You compressed it, shrunk. The distance decreased. That's why it's negative. The other one, you stretched it. That means positive 0.07. But I can't answer the question. Why? Because we have no idea what k is. Well, they gave us this force and they gave us that distance. There must be a reason for them. What's the significance of that? What is F for a spring? What's the equation for F for a spring? Isn't F equals k times x? Do we know what F is? 120. Do we know what k is? No. Do we know what x is? 0.025, 225. Can we find k? 120 divided by 0.0225. 5333. The book was using 3 significant digits, so 5330. All the numbers were 3 significant digits. I just didn't put them in. So if I use that number 5330 for each one, I can tell you what the answer for each one of these questions. 0.5 times 5330 times 0.035 squared. Now, did you hear me? I didn't say minus because you're going to be squaring that. When you square it, it doesn't really matter. It's going to be a positive. And if you expand that by 7 centimeters, $13.1. Okay. So we know potential energy is mgh. We know work due to gravity is conserved force mu initial minus mu final. Those are the equations I've been using. Let's put this chapter with last chapter together and see what will happen.